Complete the following. A to the third equals a squared times a to the blank. That would be a to the first, right? Because you add those exponents when you multiply. B to the seventh would be b to the sixth times b to the first. C to the sixth is c to the third times c to the third, because 3 plus 3 is 6. D to the eighth would be d to the fourth times d to the fourth. Unbelievable. Square root of 4, you could say plus or minus 2. Today we're just going to take positive versions of square roots because we're not solving equations, we're just simplifying these radicals. 169 is 13 times 13. 25 is 5 times 5. And 49 is 7 times 7. All right, let's get into the meat and potatoes. If you type in the square root of 192 into your calculator, you're going to get a decimal. Square root of 192, I got 13.85640646, and then it stops after that. I mean, my calculator rounded there. We're not going decimals on square roots anymore. We're going to simplify them using perfect squares. Perfect squares are listed here. It looks like perfect squares, but the PE's behind the thing there. But these are numbers that you can square root and get a whole number. So like 1 is 1 squared, 4 is 2 squared, 9 is 3 squared. 49 is 7 squared, 7 times 7. These are the numbers we're going to use to break down 192 until we can pull out no more perfect squares. Now, we ignore 1 because 1 goes into everything and it doesn't really get us anywhere. It's kind of like if you had to simplify the fraction 2 over 6. You wouldn't divide them by 1 because then nothing would change. So looking at 192, let's say I did 192 divided by 4. Great, it's 48. So here's how I do it. I create two radicals. 192 is 4 times 48. Cool. Now, we all know that the square root of 4 is 2, so this becomes 2 times the square root of 48, which is just 2 root 48. And you're like, unbelievable. That is great. We took out a perfect square, and we're moving on to the next one. However, 48 still has perfect squares in it. There are numbers down here that still go into 48, and we have to go until there are no more numbers except for 1 that go into it. So I know that 48 is 4 times 12. So I could be like, all right, I'm going to make 48 root 4 times root 12. All these things are being multiplied here. So when I take the square root of 4, I get 2. We're going to have to multiply it by the other 2 that was out there. So we'll have 2 times 2 times the square root of 12. So that would be 4 root 12, right? 2 times 2. And there's still a perfect square in 12. That's 4 times 3, so we'll make this 4 times the square root of 4 times the square root of 3. 4 times square root of 4 is 2 times the square root of 3, and then we can do the 4 times 2, we get 8 root 3. There are no more perfect squares in 3, except for 1, but we don't count that. So that would be our final, simplest form for the square root of 192. We got there eventually. You might also have noticed that 192 is 64 times 3. And 64 is a perfect square. Square root of 64 is 8, so this becomes 8 root 3. Same answer. Look at this amount of work, look at this amount of work. Still gets you there, but if you can find a perfect square, the largest perfect square you can find just saves you work. So like when I check in my calculator and I divide by 4 and I see 48, in my head I think, I know that 4 still goes into 48. So I know there's still more perfect squares. So I try with one of the higher numbers like 16 or 36 or 64. Just a little tip for you. Let's try more. That's what we're really practicing today. 50. You look at these perfect squares, you're like, do any of those go into 50? Oh, 50 is 25 times 2. So we'll make it root 25 times root 2. And then you square root that perfect square. The square root of 25 is 5. 5 root 2. Unbelievable. There are no more perfect squares left in 2. Now, ooh, on this one we have a number outside of it. We've kind of already done that. Again, all this stuff's being multiplied. So let's work on this 300. Anything that ends in 100, 100 is a perfect square. So let's use that. 300 is 100 times 3. Again, all of this stuff is being multiplied. So we're really doing -5 times the square root of 100 is 10. And then we got that root 3. If we multiply -5 times 10, it's -50. And then you got your root 3. No more perfect squares in 3. So that's it. 18. Which of these perfect squares go into 18? The only ones that are less than 18 are 4, 9, and 16. 16 doesn't go in there. 4 doesn't go in there. But 9 does go in there. It's 9 times 2. And the square root of 9 is 3. 3 root 2. All done, baby bird. That wasn't too bad. Oh my gosh, variables. Variables. I think the variables are actually easier than the regular numbers. So we have to do square root of 45a to the 5th. So here, we're going to put all the perfect stuff in the left radical, all the leftover stuff in the right side. If we're just looking at the number 45, I know that 9 goes in there. It's 9 times 5. But here's the deal with variables and exponents. Perfect squares have even exponents. A to the 5th, obviously that's not even. So what we do is we'll put 4 there, and that 5th A, that leftover A, boop, goes in the leftover pile. That's it. Even exponents for the perfect squares. So the square root of 9 normally is just 3. That's cool. When you square root something with an exponent, you just divide the exponent by 2. You take half of it. So half of 4 is 2. So that would be 3a squared. And then we have this root 5a. No more perfect squares in 5. No more perfect squares in a. So let's see. 3a squared root 5a would be option B. Let's do more of those. Beep. 27n squared. So thinking about 27, my brain jumps to 9 because I know 9 goes in there. 9's perfect, 3 is not. Now, as long as the exponent is even, it's a perfect square. So that n to the second power, that's all perfect. Chuck the whole thing over there. There aren't going to be any leftover n's. Square root of 9 is 3. Square root of n to the second is n to the first. Because again, we just divide the exponent by 2. So 3n to the first is just 3n, and then you got your root 3. -a times 60a to the 7th. Whoo! It might help if we write -a as -1a. That might make our next step a little easier. So I'm looking at perfect squares in 60. The only one I know that goes into 60 is 4. It's 4 times 15. A to the 7th. That's odd, so it's not perfect. If that's the case, just bump it down one. We'll put 6 here, and then the 7th one would go over here. So we have -1a times the square root of 4a to the 6th would be 2a to the 3rd, and then we have that root 15a. We've taken out all the perfect squares, so now we just need to do this -1a times 2a to the 3rd. If it helps, you can think of it as -1a to the first times 2a to the 3rd. -1 times 2 is -2. A to the first times a to the 3rd would be a to the 4th. Those are some old exponent properties in there. All right, here we go. X squared y to the 5th. It has to be even for it to be a perfect square. X squared, hey, that's an even exponent. Y to the 5th, ooh, no dice. But 4 of them are perfect. And then just 1 in the leftovers. Square root of x squared is x to the 1st. Square root of y to the 4th is y to the 2nd. And then you got your root y. Now, you might be feeling fresh right now. I think we're going to make up the most ridiculous problem in the world. Here we go. 200, a to the 11th, b to the 4th, c to the 23rd, and d to the 200th. Whew. All right. We'll put our perfect stuff on the left. A perfect square in 200 is 100. It's 100 times 2. Now let's look at the a's. Remember, it has to be an even exponent for it to be perfect. A to the 11th, how many of those are perfect? 10 of them. And then the one left over goes over here. We look at the b's, it's b to the 4th. That's an even exponent. We could put them all here. Cute. We look at the c's, it's 23. Ooh, that's odd. Just like us. So we could put 22 of them there, and then one gets left over. And then the d, it's 200. That's an even exponent. Put them all there. I ran out of room. All right, the square root of 100 is 10. And remember, when we square root these exponents, we just divide them by 2. So it was a to the 10th. That'd be a to the 5th. b to the 4th becomes b squared. c to the 22nd divided by 2. c to the 11th. And then d to the 200th, you divide it by 2, and it's 100. And we have the root 2ac left over. Wow. And that's as ridiculous as we could ever get today.